So we briefly saw yesterday that there's a place where we can upload an OpenC script to define our structural model. But so far we have not defined what this structural model is or how to write this OpenC script. So if you're already coming from a structural engineering background, then you probably would have used OpenCs or at least heard of OpenCs and so on. But if you're not coming from a traditional structural engineering background, then it's unlikely you might have used this software. And so we wanted to make sure that you have a complete picture of what this OpenC script should be. So Quant should be going into detail to show how to write this script, or like how to put it together so that you can define your building model and so on and so forth, right? So now we will probably go to through the Hydro application, try to run a simulation so that you get started, which is something we did not do yesterday. And we'll try to look at the preferences, how to uh, set up the HydroUQ, because if you probably have tried to run it, maybe it did not run, or it might have run, or you ended up with problems. I don't know, but I didn't hear anything, or everything ran very well, which is also good for us. I would also share with you a GitHub link, GitHub repo link, which is essentially has the files for the tool training, and this would also be made available under documentation. I just sent it out in the chat, so you can probably have a look at it and try to get it from there. So first, let's start out with that. Let's try to define how to set up the HydroUQ, right? So probably you might have already installed it. Uh, Let me just share my screen, and so we can get started. Would share the entire screen, but if it's looking small, please let me know. I'd be happy to enlarge it. So the first thing that we want to do is we want to go into the HydroUQ application if you have already started it. So if you already started the HydroUQ application, then on the file menu where you can see the HydroUQ, you'll have something called preferences. So that is where you would be setting all the HydroUQ settings as to what should it do. I think Sangri and Akash gave an overview yesterday of like what happens when you submit a job, what's going on with it, and so on and so forth. This is where you kind of make the settings of what happens in there. So first thing is you want to set the path for the Python. This is if you have already Python installed, then it's going to set it automatically. Or if you're on Windows, it also I think it comes packaged with the installer with the zip file, and it sets it for you. The local jobs directory and the remote jobs directory are the ones where the file is created when you create a job. So let me open mine. So let's say I have in my documents, I have something called HydroUQ. So you can see that users Ajay, Bangalore, Harish, documents has HydroUQ. So that is where you will find all the files. So there's a remote work directory. So since HydroUQ does not allow a local run, you probably will not have a local work directory, but since we are running remotely, it goes into the remote work directory. So that is where all the files are created. So for example, when I try to do a get from design safe, okay, I need to close this in order to do that. So you'll see that 4 files are downloaded when you try to do a get from design safe. That is the Dakota error, JSON out, and tab. So Dakota.json is nothing but the input file, which includes all the information that, okay, so this is probably different. We'll try to open that up, but that has all the information in there. So let me just try to, so that's where you will find all the files that are created by the app. So if you go to your, I think in the Windows, it is again documents, HydroUQ, remote work directory, or in the Mac, it's again your documents. That's the default one that you will choose. You can obviously change it, browse it, and change it to a different one, but you can probably just leave the default in there. The next important thing is this Tapis app. So what happens is once you submit a job, this goes to the TAC, which is the design safe cluster. And there's something called a Tapis app, which is something like you can think of it like a shell script that goes one step at a time, and which is going to run the job on the cluster. So the name of this app is Olaflow Dakota. For example, if you go to our CFD notebooks, I'll come to that in a minute. So just for somebody who is not much familiar with the Tapis app, so in our SimCenter webpage, you can find learning tools. there's something called a CFD notebook. And here, if you try to you can access this at the data from design. Say if it opens up a Jupyter notebook, I'm not going to try to do that now because it can sometimes ask me to log in and stuff like that. So we'll not spend time there. That is where you can probably learn what this Tapis app and what the name of this Tapis app and things like that. So the introductory lecture itself introduces to these concepts. So if you want to learn more about that, I would probably that's where I can direct you to. The more important application is this remote applications directory. For example, here you can look at it. This is if you have a HydroUQ installed now and try to open it, you will see that by default it has a different place. I think it's something like slash home slash tg something something something, some cryptic name is what is probably there. So for example, if I try to do a reset, right? So if I reset to the default, so this is what you would be having there. So you would have something like work200477 TG457 Stampede something. So this is the actual one that the Sim Center uses. So this is called a backend application, or you can think of that as this is the brain of the HydroUQ. So when whatever you're doing in the front end creates a job that sends it there. And this is what is parsing this input file and starting your simulations and running, creating the input files for your simulations and so on and so forth. You can think of this something like a brain for your HydroUQ, right? Okay, I didn't see that. And so for this workshop, and let's say for probably for the next 15 days, I'll keep this active. You can just change this to work 207231. I'll just post this into the chat window so you can also change it if you're trying to run the HydroUQ. Because this is slightly a little bit updated and slightly modified for the workshop so that you can run things. And once you're done with the, probably for the next 15 days, since our engineer is now in Ireland, once he comes back, probably I'll remove this so you can just then, after 15 days, if you think your jobs are failing, just go and do a reset and this should start working as well. And even this is working now, but I have some customized some things for the workshop. So probably for the next 15 days, you can keep the this one. And once you change it, just make sure you press the button save so that the settings are saved and it's going to access this backend applications or this HydroUQ brain rather than the default brain, right? So that it has some additional modules in there that we can play with. Okay, so second thing, now we want to have some files to work with, right? So we know how to set up HydroUQ. So now that we have set it up, let's try to run some kind of a simulation in order to do this thing and try to run a simple job. So what I would suggest you can go to the GitHub page. So I already posted the GitHub link here. So you can go to the GitHub page. There's like lab 1 and lab 2. So we were supposed to do lab 1. Yesterday, I'll go through what is there at the end of this session. But let's focus on the lab 2 so that we can try to get some job running quickly. And you'll be able to at least run one of your jobs and then probably you start to get a feel of it, right? So there's a dakota.json file. There's a pprocess.csv, wmdisp, and wmheight. So these are just 4 files you can download. So you can just go here, either you can fork the repository or you can just go here and download the zip. So forking is probably better. So when I make an update, you'll also be able to get these updates in there rather than having to download a new thing every time and trying to say version 1, version 2, version 3, right? So fork is probably much easier. So just download the lab 2. And I already downloaded that here. So I have it in my desktop here. So I will not do the download again. So I have my lab 2 available here. So what I'm going to do just to start my job is I'm going to go here and I'm going to open the file. So from the file menu, I'm going to open it. So probably with your Windows, it's a slightly a little bit different, but you can still find your file menu, I would hope so. And there I'm just selecting lab 2. I'm going to select the dakota.json file. So there are 4 files. One is a .csv file. There are 2 txt files, and there's one JSON file. Okay. So we will try to go through what these things are and try to understand the what these files are giving us in there. So dakota.json is essentially all the input and output files for us which are saved are in this JSON format. Okay. But then, for example, we might be selecting several other files that go in along with it. For example, if you're defining a geometry as an STL file, this is also going into the server from your local computer. So all of these are put together in a single place. So now this Dakota.json file is calling for other files. So I just need to set the path for that. So I'll go back to this folder that I had and say, okay, look in this folder for the other supplementary files that you need, right? So it's going to ask for this message that says that, okay, hey, can you set the work folder? That means that this Dakota.json might have other supplementary files that you need, and you want it to point to this particular folder. You can just give cancel and it's just not going to load these things. For example, let me show you what happened here, right? So let's go to the event. If I go to my boundary conditions, I can see that there are two of these files. So there's the same path that I looked at. My desktop, Hydro TT01, Lab02, WM disk, and WM height. Right. So these are the two files that are going in there. And also, for example, when I go to my post processing, okay, so that it doesn't load. Okay. So these are the files that it is trying to find. And so we just want to give a path so that it's able to find these files. So when we run the job, it can send these files as well, right? Okay. So now let's try to go back to the setting. There are a couple of errors that are happening in here. I just want to point it out. And we are working on it. For example, let's say in my own HydroUQ, I have raised issues to kind of fix these things in the last couple of days, whatever we found. Because of the tool training, it's not been fixed, but over the weekend, it'll be fixed in there. But just make sure everything looks good. So what we have simulating here is a small wave flume and a small building in a wave flume. So that's why the building height is just 1 meter. So if you think of, okay, hey, why is there 3 stories and just 1 meter? That's just a small miniature building inside the wave flume, right? And so we say that the width is 1 meter, depth is 3 meters, and plan area is 3 meters. It's at a x coordinate of that is 47, and y coordinate is 0. Okay. So here we are going to define. So this is one thing that is not being input. So it somehow there's an error. So there's an error that it's not reading from the input file, but we'll correct that one. So yeah, so there are 3 stories, and it's basically, and we are defining one random variable for the floor weight. So we can see that the random variable is also defined here and directly imported in there. So just be careful to check the story height. When you're sending the job out, there's an error in there, and we'll fix that out immediately. So then the finite element settings are automatically there. EDP, RV is there. So now we need to look at the event. So the most critical part is the setting up the CFD simulation. So if we are looking at our simulation type is CFD with a waveflume digital twin. And so then we look at the bathymetry. I'm using a standard OSU flume. So if we go back to our documentation, right? So I'm trying, I keep going back to the documentation even yesterday, just so that we are able to link things to it. You should be able to find the, let it open in there, and the user guide, hydro events, and geometry, right? So if we look at the bathymetry, there's a wave flume as well. So you can see that there's a standard wave flume, and these are the coordinates of the standard wave flume. So basically, like if you look at the wave flume, they're defined as like the points of the cross section and what is the breadth of this wave flume in a way. So that is how I'm defining the overall definition of the wave flume. So you need to give the x1, x2, x3, which makes the outermost geometry of the wave flume, and automatically this is going to create an STL file so that you can, OpenFOAM can mesh with it. Any questions?
Just a quick question. So
yeah, sure, definitely.
You were able to specify longitude or latitude? Latitude, I think. Like, what does that actually do?
Yeah, so actually this is a small thing that we need to change as well. Since originally some of these things were started out with a earthquake engineering background. So latitude, longitude is primarily when we are using the bathymetry, or like when we are taking things from the shallow water solver. The latitude, longitude is the place of the building. So the general information here is the place of the building on which we want to get the response. So this is the location of the building. But for the flume,
so it affects it, and like the earthquake can affect the building as well in terms of how close it is to the earthquake.
Right. Right. Yeah.
Gotcha.
Here,
Okay.
basically, like we have the coast, and we want to look at a response on one particular structure, which could be the critical structure or high-rise evacuation structure. Then this is probably going to be this building on which we want to find a response. So the general information defines all the information about this one building on which we are looking for the response. And so
Okay.
basically latitude, longitude gives the location of that. In a wave flume, since you don't have a latitude, longitude, this automatically becomes the X and Y coordinate in the flume in a way.
So that doesn't quite work, does it? Well, I mean, the other thing too, I was gonna say is like it could have an impact on Coriolis, but for
Right,
tsunamis, that
right,
doesn't
definitely.
play in, but it will for storm surge and things like that. So,
I see.
but not locally, and that was why I was a little curious. So
Okay,
anyway,
okay, I see. Uh, yeah, so in the documentation, again, like we've given the definition of how to define the wave flume. If you're basically like kind of for defining a wave flume, there's also like if we go back to the event, instead of a standard wave flume, you can say, I want to give my own wave flume, right? I want to define my own wave flume because my experiment is slightly different than what everybody else is doing. And in that case, again, you just need to give these coordinate X and Z coordinates that are there that kind of make out the segments of the entire wave flume so that so that we are able to trace an STL file out of it in order to build a geometry there, right? Okay, so let me go back, put it back to the standard wave flume so that I don't have to fill this table. We'll try to make sure that we can probably make it more user friendly if there are some suggestions out there. So we don't have a shallow water CFD interface here, but then we can add in buildings in here. So this is one thing that is somehow not getting, there's another bug that is there that we have to take care of that is not getting loaded. So as we discussed yesterday, we are defining our buildings here. So we have geometry and we have buildings and specimens. So we said there are 4 different kinds of buildings, and we are just giving a code to identify each of them. So this is a building where we have a building, want to get a building response, or a building where we don't want to get a building response. So these are other buildings around the actual main building which could influence the flow, right? So you can define multiple buildings in there in the entire thing. There's probably one big structure on which we want the response, but there are other structures around it which would probably influence the flow. So we want to also add these structures into the entire domain so that the flow is captured accurately. This will probably be changed later in the next version, but for now there are 4 codes. One, as we saw yesterday, the -2, -1. Anything less than 0 says that this building is one on which we need a response, and anything greater than 1 is where we say that okay, there's a building which is just around there, but we don't need a response on it, right? And so then we define the center of this building. So I'm just going to put in a number that works. That is from the example. And also we need to specify the parameters. So if it's a building on which we don't need a response, then this is not critical because sorry, if it's a building on which we need a response, then this is not necessary because this information is going to be read directly from the general information. But if it's a building on which we need a response, then we have to give our length, breadth, and height. So I'm just going to put it there just in case, length, breadth, and 1.247. So this is the same information that we have given here. So the length or the depth is 3, which is along the direction of the flow. 1 is the width of the building and height of the building or the specimen, let's say. Let's not call it building, maybe the specimen that we are looking in the flow. Alternatively, if we have a -1 type, is essentially where we can, instead of defining these numbers, we just say, hey, here's my STL file for the building. Or, this can be like a complicated geometry, like I was saying yesterday. We are working with Tori Johnson from US Naval Academy, who wants to do mangrove forest. So instead of a building, we have like a mangrove tree, which has a complicated geometry in there. So you can just upload this STL file, and automatically this STL file is going to be moved to the right location so that you don't have to worry about that. So, right. So then the meshing, we have like I discussed yesterday, we have 3 different types of meshing. For this example, we'll just leave it the HydroUQ measure, which is the inbuilt measure, which is good for a beginner to start exploring. And then probably if you're a very expert user, then you want to make your own mesh with one of the commercially available tools like Fluent or Gmesh or one of these, so that we can import into it. So that gives you a lot of control over the meshing. Then you don't have to define the geometry either. But here, let's leave the HydroUQ measure. and material properties and initial condition. Initial condition is I have this entire domain in which I have air. So for example, my alpha value of 0 is says that the entire domain is filled with air. And then I define a small box and say that in this box I have water. So I'm just saying the alpha value is 1, which is saying that this box has water. So automatically some kind of initial condition is defined with the flume having some water and some air. And finally, the boundary conditions. So here we have defined 6 boundary conditions. There's a small bug here that will again, that has been noted. So if you try to import multiple times, it adds on these boundary conditions rather than adds it new. So just be careful that you're giving the 6 boundary condition. So here we have the general moving wall and the flume moving wall. So the flume moving wall, essentially, if you choose that, you can directly bring in the, if you're working with Oregon State University, and if you have done some experiments in there, then you would have the moving wall displacement and the height of the water. So the wall displacement essentially says in the large flume, which is like a channel flow, on one side you have a wall that is basically moving back and forth, and this back and forth movement causes the water in the channel to also create a lot of waves, right? Like we were seeing in the video yesterday. So this moving wall file is essentially has information about what is the displacement of this wall, and height essentially has the information as to what is the height of the water at the moving wall. So the height file is not necessary. It essentially allows OpenFOAM to calibrate so that it can give the right wave profiles. The only thing that is mandatory is the moving wall displacement so that you can get the right boundary conditions on one end of it, right? So let me just open the file. So these were the files that were loaded. So WM disp and WM height. So if you're looking at the Oregon State University Flume, then essentially you don't have to do anything. You just bring the file from your experiment, select OSU and just select it and it's done. But probably not everybody might be working with the OSU Flume directly. So you might have files in different formats. So there's also a general Flume, which is defining a general, let's say, SimCenter format in which you can give the files to the HydroUQ. So here essentially the displacement file, first number is the frequency, and the rest of them are the displacement of the wall. So based on number of entries, I know what's the time. I can create a time series. So this is essentially, you can think of it as a time increment, right? So at what is the time? So this was at 0 time. This is at 0.1, at 0.2 seconds, 0.3 seconds, and so on. So the first is nothing but the frequency. And similarly, when we take the height, the first number indicates what is the height of the water level, and the rest of them indicate what is the delta H of the water level at the flume boundary, right? So, I mean, I would be happy to elaborate on this if somebody is interested or would like to use it, but just in the keeping time in mind, I would let's move ahead, and I just leave the pressure as a default choice. For the rest of the bonds, so this is my entry exit. I just leave as an inlet outlet, and top is the inlet outlet, which is my atmosphere. For the other three, which is the bottom wall, right and left wall, I just leave it as a wall with no slip. So we already discussed yesterday, what are these wall boundary conditions, what is the atmosphere, what is inlet outlet, and briefly we have discussed it, but we can always go back into the details of it to discuss, look at it more. So finally, solver, I'll just run it for 3 or 5 time steps so that we are able to quickly see the results, hopefully before the end of the session. I mean, you can probably run it for much longer. So one thing that when you're running it is probably your right interval would want to be much higher. Probably I would just put a right interval of 0.1 rather than this. But since we want to see some results here, so I'm just going to keep the right interval and the time interval to be the same. So generally, right interval can be 1,000 or 10,000 times more than the time interval. And generally, since we have a adaptive time stepping, at every right interval, it has to write. So your right interval is somewhat a maximum limit of what your time step could be when you're running these simulations in a way. And I'm going to just divide into 3 domains here and leave it to run. So I start from 0 and end up at 3 seconds. And I think that's like 3 microseconds. And my time interval is 1 microsecond at which I'm going to write. So it's almost nothing, but we just want to try to run this simulation and be able to get the results back before we end the session and look at how to get these things back, right? So that is the reason I'm just going to run it for a couple of time steps and run it through that, right? Uh, okay, so now so I'll just select no post-processing for now. And all I need to do is I need to go and log in. So I hope everybody, all of you have a Design Safe account now. And you can just log in with your standard Design Safe account. And even though you log in with your account, it is not going to be using your allocation. You might have allocation either as an individual, as a free allocation, or if you're a faculty member, or if you're a researcher, then you might have special allocations on Design Safe as well, but it is not going to use those allocations. When you're running a job, it runs the sim center location. So pretty much you have unlimited resources here. Uh, you can uh, you can use up to 62 processors per node and as many nodes as you need. Only limitation is that your maximum time limit is 48 hours. We are working with Design Safe to make sure that we can extend this and have a lot more time go to like at least 120 hours or so. But still, we are still working on that. So at the moment, if you run any job after 48 hours, it is going to get killed, right? So that's the only limitation. You don't have any other limitation in terms of number of processors and nodes. Of course, each node has only 62 processors, but that's a limitation. But you can use more nodes if you want to have more computing power as well. So one thing to be careful when we are trying to run a job, I hopefully submitted it. Did I not submit it? Okay. Okay, yeah. So if when we run a job, one thing to think about is the processor, right? So this is kind of governed by the number of samples that you're using in your UQ tab. So let's say if I change this to 8, and now let's say I give it to run, it's going, where did it go? Yeah. Now you can see that the number of processors changed to 8. So you need at least as many processors as number of samples that you need here. Okay. So that is the only thing, but also you need to be careful about what is the domain decomposition you're giving here. As long as this is less than the number of processors you're using, less than or equal to, that should be okay. For example, let's say if you say I want 20 processors, but I divide into 32 domains, it only finds 20 processors to send your job to, but then 12 of them or more are there where it cannot send anywhere, right? So this can be a problem. So you need to be just careful of how many domains you're dividing. I mean, I think in the next version, I just also will make sure that we are connecting these things, and it indicates you that, hey, you're using less number of processors or so, so that you don't have to worry about this. Yeah, are there any questions? Yeah, yeah.
Do you notice that I unmuted? Sorry.
Yeah, no problem.
So
So I thought probably there's a question. Yeah, please.
yeah, that's okay. So the number of subdomains means does that actually truly map to the number of cores that you have available? Because
Yeah.
it seems like because OpenFlow can actually run on multiple nodes, like MPI wise, right?
Right. Yeah.
So I guess I'm trying to understand, like, if I'm going to set the number of subdomains,
Mhm.
number of processes per node is probably going to depend on the machine I'm running on.
Right.
But then how do I go, so you've only set the number of nodes to 1 right now.
Right.
I can set it to something bigger than that.
Yes. I mean, it doesn't matter.
Like, what I guess, but what's the recommendation on how to set the number of subdomains versus, this it's a load balancing question I'm trying to ask.
Right.
So,
yeah. So the two things that we have done here. One is basically the Scotch method that OpenFlow uses, does some bit of load balancing automatically. So what it does is when it's dividing these domains, it tries to ensure that the number of faces that are intersecting between the domains are as minimal as possible. So because if you have like a common face between the two domains, then that's a common cell and a common face center for which it needs to do the communication. So firstly, it tries to minimize that. So some bit of load balancing is already taken care a little bit in there. Second thing is, irrespective of how many nodes and processors you choose, it is treating, TAC would treat each of these as a separate MPI job. So you'll probably have some kind of a communication between each of these. So it's going to just treat it as one MPI job. So it only looks at it as, are you looking at one node and 20 processors, or are you looking at 4 nodes and 5 processors each in a way? So both of these are kind of equivalent there because each of these is basically for TAC, it is like a 20 MPI task, nothing more than that. So that's where kind of, I mean, if you can use one node and if you can get up to 62 processors, then I would go with one node and 62 processors rather than spreading them across the nodes in a way. That would probably be the recommendation to go with. Also, it's much easier to find things if you're looking on one node, and your job might start much faster than if you're trying to get processors on multiple nodes in a way.
Maybe an easier question is like, what would you suggest to someone who didn't know?
I would just say
other than like that they were running on, one of the TAC machines. I think it's difficult to know like what one should do.
Right. So, I mean, my general recommendation for somebody who is starting up would be just leave the node number as one, unless you're looking for more than 62 processors. As long as you can work with 62 processors, leave it as one and just put the number of processors you need. But if you're looking at more than that, then you can probably change the node numbers and number of nodes equivalently to it, I would say. So it's basically 124, then just put it as 2, put it as per node as 62, and then automatically takes care of this in a way on the back end.
In number of processors per node, you're talking about cores on a node?
Right. Yeah.
Okay. So I'm assuming there's more than 8.
Right. On each processor, you have more than 8. Yeah.
So like 20. Can't actually remember what's on the machine now, but anyway.
I can have a look at that. I can kind of look at that and get back to you with what TAC is offering there in terms of that. Just give the exact number.
63. Well, that's a funny number. Yeah.
Yeah, that's what I meant. It has 63. Yeah. One is reserved, I think, for a master thing, and you can use a maximum of 62. That's what I remember. And that's why I was saying 62 is probably the limit for one of them.
I guess, like, for those of you that aren't computational scientists, making sure to stick to that number is kind of important, regardless of whoever says that there's more threads. Right. Hyper-threading is not a thing. Don't do it.
Yeah.
It's not a thing, but anyway.
Okay. If you just at the moment, you have to be manually careful that the number of subdomains is not more than the number of processors you're calling for, in which case the job will probably fail and you'll get a failed message in there. So once then you just need to give let's say some name, lab 2, right? And I'm just going to send it out. I'm just going to give it an hour. Probably this will get finished in 5 minutes once starts to run, but I'll just put an hour in there. I mean, I would generally keep the time. So generally a good practice is to keep the time as least as you need. So that when it comes to allocating you will probably not be in the queue for a long time. If you say, I need 48 hours for a job that needs 5 minutes, then probably you'll be in a queue for much longer than when you say it probably needs just 10 minutes or something like that. So just be careful, like probably after you play around a few times, then you know how much time your simulation will take. Maybe you want to add a factor of safety a little in there and then just throw it out so that you can ensure that the job at least finishes before you can move ahead, right? So, yeah. And so now if we just use the get from design safe, that is going to get you the job status. At the moment, basically it is still queued there. So you can just refresh it and try to find out. Also, another way to find the status of the job is you can go into design safe. Okay, I've logged in here. So let me go to my dashboard. So here also you can see what are the jobs that are running, right? So this is the job that I've started today. So in the morning I was trying something, 2 of them failed. So this is the job that is queued. Once the job finishes, you can press the link to output and you can go to the output folder. But if it fails or if something else happens, then you probably don't have an output folder into which it would create these files. So this only works in when you have a job that is finished. So, and if it's work, let's see if something is there. Let's see. Okay. Yeah, okay, so that didn't open, but also if you, I showed you yesterday that you can go to my data and you can go to archive and jobs. I mean, the painful thing sometimes is that you cannot download individual, you cannot download folders from Design Safe, but you can only download files. So what we are doing is we zip everything in there. So let me go to a job that's finished. So, and hopefully this is a finished job. So then if you look at the ID of the ID of the job here says 9411 something here, 9411C. So in the archive folder, you can just find job dash 9411C. So it's basically job dash 1 to 9, then A, B, C, D, E. So 9411C. So 9411C, that's the one that we have yesterday, right? So if I look at it, hopefully, yeah. So now you can see here will be all the files once the job has finished. Let's see if started running. Now it's been the queues have been really long since yesterday night somehow. So that's why I just ran something so that we have something to see in there. So the temp folder essentially has all the files that come back from the structural response. So this is a dakota.json input file that we had sent, right? So everything when we wrote I need it, I should have captured it. Let me do that. Let me show that to you. And then essentially all the event files are zipped into the event files.tar.gc. So if you want to look at the open form file, so that's the one that you want to download. So it's kind of easier now because everything is at tar.gc. You just download once rather than having to download individual files. And so now let me open this thing. Okay, so now if I open the tar.gc, okay, so this has all the files that you can look into. So this has the zero folder, the constant folder, the system folder that was there that we created for the open form run. There was all the logs that are there. For example, the block mesh log. So these were all the logs that were created. So when I ran block mesh, you have the log that is there. You can see if something went wrong. Or like, for example, let's say the Olaflow DYM log is essentially the log that was created when the solver was running, right? And similarly, you have so each of these operations creates a separate log. So you can look through them, and if something is not working, you can see that, hey, this is where my job failed. I mean, if it fails in the event, if it fails elsewhere, then you probably also know. So one other place to look for the bug is, I mean, if something goes wrong, you get a failed message, are these two files out.out and .err, right? I mean, when you're trying to do a CFD, most often this happens, you will get some cryptic messages, and these are files where you can look at it and try to say, hey, this is my error message. So now let's see what went wrong in there, right? So if you open the out file, so you'll see what everything that is being done here. So there was we will see this template.dir.zip was sent from our local computer to TAC. Now this was uncompressed. So if you look at it, this uncompressed, when you uncompress it, it has dakota.json. That's our input file that was created. Then we have also these WM disp and WM height. So these were two files that I said I didn't send a post process, a P process last time. So these were the files that are all sent from your local computer. So it's unzipped, and then it starts to read all the variables, does a lot of things. For example, open form path is loaded, pre-processing starts the mesh, starts material, pre-processing, sets up variables. Then we are doing the combining the STL files that were created, block mesh is running, surface, feature extract, snappy hex mesh. So we are creating a zero folder here and decomposing the domain and finally starting CFD simulation in parallel. Then once the CFD simulation is done, then it starts the Dakota and open form. So you can see that it is starting in there. And this is probably one place where there can be an error where an open form event is returned to event.json. If your open form simulation did not run correctly, then we would not have the body building forces. So if you look at our log here, let's go back to our log. Sorry, this is probably a little bit small. Let me try to make it big. Let me try to open it in something else. Mhm. Now probably this is a little more visible, hopefully. So if you look at it, forces or building forces are being written. So when the solver is running, it is writing these building forces at each time step. And now later this is parsed and sent into OpenSeas. I think Quanchi will talk about this and how it is going into OpenSeas and what OpenSeas is going to do with it. But this is where the building forces are being written and so on. So for example, now if you don't have any building forces at all, or like for example, the event did not run, the open form simulation did not run, then you will not have these, which means this is starting to going to give you an error because there's nothing to write there, right? So unless the event was there, unless the open form simulation happened, there's something to write, else there's really nothing to write for it. And then it's going to start your Dakota where you can see that, all the Dakota was being run here, right? So there's also another file, I think .err, where which also it has a lot more details in there. So for example, this has a lot more details about this is like everything that is being executed on the shell script is being written out here. It's like let's say giving a print statement. So when you give a print statement, it comes on your screen. But here, since you're on a supercomputer, you don't have a screen to look at it. It basically writes out everything into a file that you can go back and see. Okay, hey, what is happening in here, and where did something stop? Right. So it's going to write some error somewhere where if it's not going. So for example, here invalid requirement. So so we were trying to upload, let's say, install a particular version of Mesh IO, which is a Python library, and there was an error that says invalid requirement. Okay, that's a bug for us to fix, right? So this is where you can find something that some errors that could be happening in there. So that's one issue that we have been having with Python is something is working and then there's a new version of the library and then the old version is not working. So right, so but then so you can see here. So here is basically the entire thing that we are doing here. So this is the what is creating all your open form files to run the simulation. So if you look at it, so this is the work to Ajay Stampede's backend application create event processor.py. So that is the, for example, if you go back to our preferences, we had set this path work to SimCenter backend applications here, right? So if you look at it, that is what it is calling here. So that is where it is going to find, let's say, the brain of the HydroUQ in order to do some simulations, right? So that's on a TAC supercomputer. So it's going to call that from Stampede and call this processor.py, and -b essentially is the input file. So you can see that this is the dakota.json file that is being sent as an input file. Along with it, it's also sending several other things like what is the path of the folder and so on. But this is where things are happening. And then essentially the HydroUQ pre-processing is complete. We started the case run. And so essentially then we are running the OpenSeas and so on. So these are two files you can look into where you might have some errors and something doesn't work. Then this is where you can find out what happened in there, right? So let's go back to our event folder for a moment. So this is the event folder that we downloaded, the EVT files that we downloaded from design save, the EVT files.tar.gz. So you can find all the post-processing. For example, somebody was asking about the forces yesterday. So here you have the post-processing folder where you have the building forces that are run and forces you can find. So forces.dat is what OpenFOAM does. It takes the entire building as one single patch or a face of the building as one single patch, and it's going to integrate the pressure over this patch. So that's what forces would be. Forces._bins, what it does, it basically takes each of these floor as one single patch and integrate. So you get like some kind of a floor loading. I think Quanchi will talk a lot more about it. So I'll leave that to Quanchi to discuss this in the next coming session. Right. I think we are probably running out of time, I guess. So yeah, so that's the kind of where you can look at all the forces. Let's try to go back and see if we are off the queue. Okay, so sorry, we are still queued. Let me try to pull back something that is already done. So for example, when we, so you can just refresh and that's going to give you the status. And I'll just pull out something that's finished and we can, so you can do retrieve data from here. And what the retrieve data is going to do, you can see the dakota.json, dakota.tab, dakota.tab.out, dakota.err is being downloaded, right? So it's asking me for all the other files I don't want, I can just cancel. So it says work directory has not been set. You will need to manually update the required files for EVT again. For example, our boundary condition files that were there. So let's go back to the HydroUQ. So we were able to populate these results and get some numbers in here, right? So we're able to do something in here. But then if you go to EVT now in the boundary conditions, you see that Yeah, so this was a bit of an error that is there. So it was not able to select the boundary, get the right boundary condition here because we did not allow it to find these files. So that's one thing that we need to think about. But then you can just pull back all the structural results, get some of these things and like peak floor acceleration and so on. I think Akash was talking about this yesterday, and Kwanchi will probably talk about what this result tab means and what are you seeing here in a way later in a few minutes from now. But that's how you can pull back these results. But one thing, let's try to see what happens when we try to give it a run, right? So let's say I go to run. Now let me try to capture the file. So now I'll go back to my documents folder. So this is the HydroUQ folder. So this is the one that we had set here. So if you remember, we had set this remote jobs directory, right? So remote work dir. So I'm going to HydroUQ and remote work dir. So why do I want to do this? I want to just capture the files that I'm getting. So let me make sure I can copy paste immediately. So it's going to create something and it's going to delete everything immediately. So let's say Hydro Lab 3 or something, right? I'm just going to send something out. Maybe I'll do something for 1 minute, not to waste time. 10 minutes or 1 minute, okay. One processor, one node, 1 minute. So now if I give submit, it's going to create this folder. Sorry, it somehow crashed. Okay, let's try to restart this thing. Okay, so now let me just open the usual JSON file that we were working with. I'm just going to load the input file just to start a new job. Let's delete this one. We want to capture the temp folder and see what's in there, because now this is probably crashed. It's probably going to have a empty Dakota file in there. We don't want that. Okay, so let's try to. It doesn't really matter as long as things don't crash. So this is probably the reason for the crash. I'm not really running a job, so I'm just going to give some random inputs because we just want to capture a file. I'll show you what I'm trying to capture here. So now, so when I give run a design save, it created this temp folder. I'm just going to copy it here. See, it deleted that immediately. So it created all these input files. It's going to zip it up and send it to TAC and then delete it on your computer. So I just want to make sure, just to get an idea of what is going out. So you can see that there's a dakota.in, which is like some kind of a log file, and and there's a dakota.in which has all the information about some of the UQ parameters that we are interested in. And there's some log file that was there. So essentially, when you said run, this was something that was happening on your computer to create these files. But then there's a template dir.zip. If you remember on our design safe as well, if you go to the temp thing, you can see that there's a template dir. So that's the one that we have sent. After the processing, it again zips it back with few other files in there. So now if you open this one, we see that there's a dakota.json. So this is our input file. So this whatever you have given in the UI, this is where it's being written into a JSON file. So it's writing everything into this JSON file with all the information. Like for example, let's say what is the building type? I want to I'm defining it manually but not parametrically. Building table, I was giving 1111 something. Domain decomposition, what the domain decomposition. So you can pretty much relate to whatever inputs you are given if you're getting the right things here, right? And so then it also uploads the files that we are sending. So we said WM disp and WM height. We want to give these things. So these are also zipped in, and it's going to create few other files along with it. All of it is created into a zip folder, and this zip folder goes to TAC. And once on the TAC, it unzips itself. We saw in the log here, I think, right? So if you remember, we just saw in the log, I think this was an out file, I'm guessing. Yeah, so if you can see, the archive template dir.zip went to TAC, and it is being uncompressed here in order to again use these, get these files and use it. And so that's what's happening in there. And so once these files are unzipped and something starts, it again goes to that that brain that we have, like, or the HydroUQ brain, what I would say, and uses some Python scripts and several other scripts in order to generate all the input files and run your simulation. I mean, I just wanted to show you this just to make sure that we have a general overall idea of what is happening in here and how to work with it. And I think we are probably out of time, I'm guessing. So, right? Or do we still have some time? Mm, okay. I think we are probably at the end of the session. I think Quanchi's session should be starting now in a couple of minutes. But yeah. But Matt, how much time do we have?
You went over a little bit. We were supposed to be on a break for the last
Oh, okay. Sorry.
few
Sorry. Okay.
minutes.
So then I can stop here. So that's the kind of giving a general idea of how the Hydro UQ application is working and what's happening and what is the how is the information being transferred and what is being compressed. So we already sent out a job. I think if you try to follow what I did, or if you were also doing it, and if you get stuck, let me know. I'm going to be around here, right? So we'll come back to see if this job got finished. Sorry, it's still in the queue. I think these queues are really long since yesterday. I don't know why. But if you can also give it a try with the file from the GitHub repo and see if it doesn't work or if it works. If you have an error, if it's working, let us know if it's working. If you have an error, let me know if you have an error that I'm going to help you with.